Hello, my name is James Black, and today I'm going to be talking about distributed databases for microsystems. So we're going to be looking at the evolution of how we came to microservices, rather. So this represents, in the early days, we had a mainframe. So we had the UI, we had a database, we had the application. Everything was in one big system. And this worked well for a long time because we didn't really have a whole lot of different programs going on. Programmers kept writing their programs and things just kept working. But over time, people said, we're putting a lot of load, let's start splitting this system up. So we had different ideas come out. And one of them was just to move the database by itself. So this way you could then do things like you could just cluster the database. You didn't have to have only one database, you could have several. And so that's kind of what they did, was they clustered their databases. And this allowed people to be able to access, because one of the problems with a database is if you're doing a lot of queries, you can slow down the database. And so the idea was just to keep that from happening. So then we came to the idea of, well, rather than just having a desktop application which had all the other logic minus the database, why don't where the internet's becoming a bigger deal, so why don't we just separate the UI from the business logic? And so that's what we did. So we have our three-tiered architecture. So you have your UI, your servers, your business logic basically, and your database. And this is pretty much where people are now. You still see a lot of new ideas coming out on how do we distribute. I want to have like Cassandra. I want to have different databases where I can have them be distributed, but I still want to have it be relational. And I find it interesting that people are still trying to make this work. The reason being because I do a lot with mobile applications. When a mobile user is connecting from here to here, they don't care what your excuse is. At one point, I think it was last year, S3 went down for Amazon. A lot of things broke. You had AWS had a problem in 2015 where they lost a data center in Virginia. You had Delta had issues, Southwest had an issue with a router. Things happen. I remember one time at Oak Ridge National Lab, we'd lose power to the lab because a squirrel ate into the power cord to one of the power wires. We don't test these things. When Delta had their problem, I'm pretty certain that every sysadmin in the world said, if that had been my network, we wouldn't have had that problem, because I would have been working around these things. But we don't test. When I write my unit test, I don't say, just unplug this router. See what happens during my tests. We don't do that. We expect that the network is always going to work. And that's a problem, because really we shouldn't be doing that. We should design with the idea that things are going to fail. That's a big part of the reactive architecture, is that idea, but everyone should be working on that. So one of the things about that is, so what we do then is we say, we also ran into a problem with this approach, by the way, of you have tight coupling between here, here, and here. So if I make any change in my UI, if I make any change in my database, it will change the UI a lot of times. That's bad, because I should be able to change this part here. This should serve as an adapter and to give this what it needs. You should have a very loose coupling. That way people can make changes as they need to without having to have these big deployments. Because right now what happens is, if I make a change here, then I first have to look at, okay, well, I want to make a change to a table also. I have to find all the applications that are using that table that are not mine, make sure that they all agree, and then we all move our stuff together at the same time. But in order to just make a change here, I have to do a lot of testing. I have to do all my regression testing, all my unit testing. Everything has to be tested to make certain that nothing will break. And this takes a lot of time. That's a problem, because nowadays we want to get new features out quickly. We don't have time to go through a month of testing. I remember at one company I worked at, we had, I think, the entire team, so we had 14 people testing for 3 weeks before we could move this one application into production. That's ridiculous. So what people start doing is they start to go to more of a microservice architecture. And what that did basically is you would sit there and say, okay, well, I'm going to break down my web services into smaller components, smaller deployable components. So for example, I might have my order service might be here. I might have my inventory services be here, and I might have my distribution services be here. And that way, when I make my changes just to my order, this should be self-contained, and it shouldn't affect anything else. One of the issues with doing this, though, is it should be self-contained. If they're still using the same database, then we have a problem. So even though this might be clustered, again, this is tightly coupled to this. So if I make a change to a order table here, it might affect the inventory table, the inventory services. So that means I have to move both of these at the same time. I can't just make a change here and make a change here and just move those into production and leave it alone. So you end up, what's nice is the smaller your microservices are, the less work you have to do. You should be able to move things in production from the time the developers are finished testing and they commit their code to the repository. In less than an hour, it should be in production. Really, there's no reason why you can't do that. And that's kind of the goal, is to be able to figure out how do we do that in a manner that's not going to impact the users. So you have to, so we have different ideas. So I'm going to take some of these away just to make it easier for seeing now. I like using blocks for this kind of demonstration because I think it gives a better sense, but now we have too many. So basically what I have is, I'm going to get rid of the UI also because that's less important here. So we're down to just this. Okay, so now we might have broken the order up into 6 microservices. And we might decide, these two are related. They should use this database. These two, this one, these two, this one. Okay. So by doing it this way, you could look at, well, which database is best for that need. So it might be that a Mongo database is better here, a Cassandra here, and a SQL Server here. But you can find the best database. But this is a big deal when you start saying, well, what's the best database for these services? And that's one of the things that by doing this, we're able to start looking at how can we make it work better. So now when I make a change here, I may end up making a change here, so I might end up affecting these two. So what I find to be better is generally, we'll get rid of these now, each microservice should have their own database. Now the problem is, there's different ways of doing this. You could have all the instances of microservice are using this database. You could have where all the instances have their own database. Or you could have where I'm going to do it by server. So I'm going to say that these 3 different microservices, order, inventory, and distribution, are going to use this relational database, and they're all on the same server. And so I have the same thing here where these are on a different server, so these are clustered. So in case this server goes down or is overloaded, it goes to this server, and they're using this database. I need to keep these synchronized. You run into a problem though with, well, how do I keep them synchronized, and what happens if for a little while this router was down, so this is out of sync, and these two are in sync? How do you know that? Because it's just the router that was down. You're not necessarily going to know unless you were getting a heartbeat from here, or these are going to start telling you that the database was unavailable, and then you can figure out what happened. So that's one problem with having this, but you also, if you go with by server, then you have to go with the common database, which a lot of times will be relational, which is a bad idea. So I really don't like that idea too much. So what I find works better is if you break everything down by have each microservice have its own database. Now you run into, there's two possibilities here. So every instance of this microservice could be used in this database. What that might mean though is that if they're all writing to it, you could still overload this database. Or what happens if this database goes down, you have a single point failure here, you bring down your microservice, the user can't use that service. And that's bad. So another option is to give every instance of a microservice, because now we're in containerization, so I might have 5 instances of this, give them all their database. But you don't want 5 writable databases, because then you run into problems with, well, if they're all updating the database, their own databases, and then you have to keep everything synchronized, your IDs are off, it can create chaos. Because synchronization could fail at times, and so then you have to get everything back in sync. So a lot of times what happens is, let's say these are all 3 instances of the order database. This one might be the writable database. So this one's the only one I can write to it. These are 2 read-only databases. And that way you can, if this goes down for some reason, one of these would become the writable, one of these would start to go to the writable one. An easy way to do that, I think, is if you're using containerization, make your database containerized. Then what you do is every so often, every few hours or whatever, you would actually make a new copy of this. You also have to have Kafka about though, or something like Kafka. I like Kafka. That runs in the background. That runs. So what happens is all the messages, so all the writes go into the Kafka topic. Then you'd have a program that is sitting on each of the, that's sitting and updating these. So this would then update its readable one, or you'd have a separate program that just runs by this, that's reading from the topic and updating it. There's different ways of doing that, but you want to try and make sure that they could stay in sync. Part of the reason, and then you'd want Kafka to hold on to data for about 2 or 3 times longer than what these hold on to data for, mainly because if you have to bring up a new container, this database, something went wrong and you had to get rid of the container. You bring in a new one, and then you can have it update, and then it can tell the system I'm live, and then the system can start working again. And so while that's happening, this microservice would actually have unregistered itself from the service discovery until its database is ready, and then it could re-register itself. That way nothing goes to it, and because it's not really ready. But you still have problems where routers and stuff could interrupt this communication. So what I like is you have in the same Docker container, you would have the database and the microserver. So if I have a sudden load of orders, of order processing, I can bring up new containers, and it's already fully self-contained. And then remember, I have a service running that's going to get us up to date. As soon as it's up to date, it tells this. What I know is I go to localhost port 3306 always, because we're in the same container. And so it makes it easier, because if we were in different, if my databases kept on changing ports and IP addresses, then somehow I have to let its microservice know what the correct information is, and there's room for error there. So this helps to cut down a lot of problems. And that's really the big part here, is we want to try and minimize as much as we can how things might fail, because we know bad things are going to happen. The more servers you're on, the bigger your footprint is, your system footprint. You're going to have databases go down, you're going to have SANs go down, routers. Things fail. That's just life. So, but if my client can connect to my microservice here, then I know I can work with them regardless, because there is nothing else. This container is fully self-contained. It can take care of its task. Now, it might be that this container has to call out to an ESB. There might be other things external to it that are single points of failure that may not work. This might just be a caching database. Odds are, if you're doing a store, this is not the entire database. This might be just products and orders that were done in the past day or past 6 hours. So but still, the user can get a faster response. And that's what you are trying to do, is you're trying to help the user to have the best experience possible, while making certain that your system is, so this will be eventually consistent. And unfortunately, the reality nowadays is that's the way even the newer databases are. The Aurora database from Amazon does that. You're going to have eventual consistency is just a way of life now. It's getting to be too problematic to try and go with just one big SQL Server Oracle database. So that's the approach that I think is best, is just to have them all be grouped together. And then the nice thing is that if I change the database and the application, or either one of these, I just update the Docker container. And so when the system pulls down, like let's say Kubernetes or something pulls down and creates a new image, a new instance of my image, then it's already the new changes. So these two are already in sync, are always in sync. Now this one and this one might not have the same API. There might be changes. This one might be better than this one. This one's going to have to either age out, or as you spin up new ones, you start to kill the old ones. But that's an infrastructure issue. But the nice thing is that when you bring it down, you don't have to wait for anything to. It makes deployment a lot easier. It makes updating easier. If this is developing a problem somewhere, if one of these is having a problem, you just kill the entire container. You don't worry about trying to debug it or anything like we do VMs or servers. You just kill the whole thing and you just bring up a new one and move on. It might be in a bad state for some reason. Who cares? And so that's what you do. Okay? I hope this makes sense. And have a wonderful day. Bye-bye.